Imagine a universe where energy doesn't flow in a smooth, continuous stream, but rather in tiny, discrete packets. What would that look like? For centuries, scientists thought of energy as a ceaseless river, flowing unbroken from one form into another. Picture a waterfall cascading down a mountainside, transforming potential energy into kinetic energy without interruption. This traditional view painted a picture of energy as a fluid, continuous entity, always ready to morph into a different form but never changing its intrinsic nature. But what if we were to challenge this long-held belief? What if energy, instead of being a smooth, constant flow, was actually made up of minute, distinct packets? These packets, or quanta, could shift, change, and interact with each other, creating a whole new perspective on how energy works and behaves. This radical idea, as strange and counterintuitive as it may seem, is not just a whimsical thought experiment. The answer to this question was provided by Max Planck, a German physicist, who revolutionized our understanding of the nature of energy. Enter Max Planck, a German physicist who in 1900 proposed a radical new theory about the nature of energy. Max Carl Ernst Ludwig Planck, better known as Max Planck, was born in Kiel, Germany in 1858. He was a theoretical physicist renowned for his work in quantum theory, for which he was awarded the Nobel Prize in Physics in 1918. Planck's life was deeply intertwined with science from an early age. His father was a professor of constitutional law, and his grandfather and great-grandfather were both theology professors, so it's no surprise that Planck ended up in academia. The late 19th and early 20th centuries were a time of great scientific discovery. This was the era of the luminaries like Albert Einstein, Marie Curie, and Niels Bohr. Yet there was a conundrum that plagued physicists of the time. They couldn't explain why the intensity of electromagnetic radiation emitted by a black body didn't match predictions made by classical physics. This is where Planck stepped in. He suggested that energy is not continuous, but rather it is quantized. In other words, energy comes in discrete units, or quanta. This was a radical departure from what was understood at the time. Classical physics suggested that energy was a continuous wave that could take on any value. But Planck's quantum theory proposed that energy could only exist in specific, discrete amounts. Planck's constant, a fundamental number in physics, is a testament to his work. It's a tiny number, about 6.626 times 10 to the negative 34 joule seconds. But it's crucial to our understanding of the universe. It's the proportionality constant that relates the energy of a photon to its frequency, a cornerstone of quantum mechanics. Planck's quantum theory was a significant departure from the classical physics of the time. It challenged the status quo, questioned long-held beliefs, and paved the way for a new understanding of the universe. Physics, as we know it today, owes a great deal to Planck's radical proposition. So, how does quantum theory work? Imagine a world where energy doesn't flow like a smooth river, but rather, it comes in tiny, distinct packets. This might sound a bit strange, but this is exactly what quantum theory proposes. It's a bit like imagining a staircase where you can only move up or down in specific steps, not halfway in between. At the heart of this theory is the concept of energy quanta. The word quanta is derived from the Latin word quantus, meaning how much. In the realm of quantum theory, quanta refer to these small distinct packets of energy. Now let's dive into one of the key formulas of quantum theory, E equals h times v. This formula, proposed by Max Planck, is a fundamental equation in quantum physics. But what do these symbols mean? E stands for energy, the energy of the quantum. H is Planck's constant, a very small number that's crucial to the theory. And V? That represents frequency, how often a wave oscillates up and down in a second. So in simple terms, this formula tells us that the energy of a quantum is directly proportional to the frequency of the wave. The higher the frequency, the higher the energy. This was a radical departure from the classical view of energy as a smooth, continuous quantity. Instead, Planck's quantum theory suggested that energy was granular, coming in specific amounts, or quanta. Each quantum is the smallest possible unit of energy for a specific frequency. And the energy of a quantum can't be divided into smaller parts, much like you can't divide a single step on a staircase. This was the birth of quantum theory. A theory that suggested energy was not smooth and continuous, but rather came in small, distinct packets, or quanta. So Planck's quantum theory changed everything. But what does that mean for us today? Let's take a step back and see the bigger picture. Quantum theory has fundamentally reshaped our understanding of the universe. It has tossed aside the deterministic views of classical physics and ushered in a world of probabilities and uncertainties. Quantum theory has given birth to quantum mechanics, a branch of physics that describes the peculiar behaviors of particles at the atomic and subatomic level. It's a realm where particles can exist in multiple states at once, where they can teleport through barriers, and where measuring a particle changes its state. It's a world that seems to defy our everyday logic, but it's a world that quantum theory has allowed us to explore. But the implications of quantum theory don't stop at mere understanding. It's also paved the way for technological advancements that were once the stuff of science fiction. Think about your computer. The transistors that make up its processor wouldn't exist without an understanding of quantum mechanics. And it's not just computers. Quantum theory has been instrumental in the development of lasers, magnetic resonance imaging, and even atomic clocks. Looking further ahead, quantum theory could form the backbone of future technologies. Quantum computing, for instance, promises to revolutionize fields from cryptography to climate modeling by performing complex calculations at speeds that are currently unimaginable. Quantum communication could enable perfectly secure information transmission, immune to eavesdropping. But perhaps the most exciting implication of quantum theory is its potential to reveal new secrets about the universe. It's already helped us understand phenomena like superconductivity and superfluidity, and who knows? It may one day unlock the secrets of dark matter and dark energy, or even reconcile the rift between quantum mechanics and general relativity. In summary, the legacy of quantum theory is far from complete. It has transformed our world and will continue to shape the future in ways we can't even imagine. Its implications are as vast as the universe itself. Planck's quantum theory has truly revolutionized our understanding of the universe, and its implications continue to unfold.